Out, we went to the Institute of Technology at Cranfield. Here we set up a special experiment on a planer. First we tried cutting a piece of mild steel this way, with a square-ended cutting tool. The face of the tool is at right angles to the work. And the bottom touches the work all along its length. On a planer, the work moves to and fro. To take a cut, the tool has to be lowered. Did you see what happened? Let's take a much closer look at that in slow motion. Here you can see how the chip forms. For an efficient cut, the chip should flow naturally over the face of the tool. It doesn't flow naturally here. Instead, it's being compressed, and it's tending to break up. Not only that, the bottom of the tool is rubbing on the cut surface. This is causing the tool to ride up over the work until it stops cutting altogether. The surface finish has a very rough look about it. And what about the cutting tool? Let's see if it's damaged in any way. What you see here is the bottom of the tool. Here's the cutting edge. Near the back we find traces of material from the work, material that's welded onto the tool as a result of the rubbing action. Now we can prevent this from happening by changing the shape of the tool. To do this, we're using a machine called a cutter grinder. All we're doing here is grinding away the part of the tool which was rubbing on the work. In other words, we're making the bottom of the tool slope away from the work. Now only the cutting edge touches the work. The angle formed between the tool and the work provides clearance. We call this the clearance angle. Let's see how this affects the cutting action. The tool cuts for the full length of the work. But have we changed the way the chip forms? Here's the cutting action in slow motion. The chip still doesn't flow naturally over the face of the tool. It's still being compressed and deformed. Now we can improve on the way the chip forms by changing the path that it takes over the tool face. This means making another modification to the shape of the tool. Again, we'll use the cutter grinder, but this time with a different wheel. Here we're changing the angle of the tool face. The cutting edge now has a familiar shape. Here's the angle between the bottom of the tool and the work, the clearance angle, and here's the angle we've just formed. It's called the rake angle. Let's try taking another cut. This time the chip seems to form in a much better way. But it's worth a closer look, again in slow motion. Can you see the difference? The chip is beginning to flow more naturally. And look at the way it shears from the parent material. It seems to come away along a line that's almost at 90 degrees to the tool face. Let's look at the shearing action in this model. As the tool cuts, the chip shears along this line here, but that's from the front. In this model, you can see that a chip has width, so it must also shear along a similar line for the whole of its width. If we take the tool and the chip away, this line becomes a plane. It's called the shear plane. In fact, we usually refer to the shear plane by this line here. The length of it being called the shear plane length. Here's the cutting action in slow motion again. Now, if you look carefully, you'll notice that the position of the shear plane is changing. And look at the material building up at the cutting edge. This disturbs the way the chip flows and will affect the surface finish. Remember, this surface is the result of giving the tool a 5-degree rake angle. What happens if we increase the rake angle to 15 degrees? We seem to be getting an even better chip formation. Here's the cutting action in slow motion. This time there's a much more natural flow of material over the tool face. This is a good chip. And can you see the shear plane? Again, it's almost at right angles to the face of the tool. Let's compare this shear plane with the one produced by the tool having a smaller rake angle. In this diagram, the rake angle is 15 degrees. Watch the shear plane as the angle decreases. Did you see what happened? The length of the plane, that's this distance, increased. So by changing the rake angle, we changed the length of the shear plane. The larger the angle, the shorter the plane. The smaller the angle, the longer the plane.